about rate of change. We talked about multivariable function. We talked about vector valued functions and finding derivatives of vector valued functions. Well, we've been talking about multivariable function for a couple of days, and we haven't really talked about calculus other than limits, which is really our backbone. So today we're going to talk about rates of change. So with a single variable function, we talked about how the function changes as our variable changes. Well, with a multivariable function, we have more than one variable. So the idea of rate of change of our function with respect to a variable is kind of a bigger concept. So what we're going to do is look at the derivative, the rate of change of our function with respect to one variable while we hold the other variable constant. That's what partial derivative means. We're going to take a derivative with respect to x. While y is constant, we'll take a derivative with respect to y while x is constant. If we have more variables, we'll keep going. We'll talk about chain rules. We'll talk about all of our different differentiation rules, and then we'll start using partial derivatives to actually do some interesting things with these multivariable functions. Maximize, minimize. We'll reintroduce vectors into our analysis of these multivariable functions, and we get some interesting things when we talk about surfaces and vectors and how they relate to each other. All right, so today we're going to talk about the first partial derivatives, or partial derivative, and we're going to say of z equals f of xy. We're going to make our definition of our partial derivative. So this is our definition. We're going to write. I'm going to give us our notation first. There's lots of ways we notate our first partial derivative with respect to x. We're going to write all these different things are equivalent. F sub x, you'll also see it written as f sub x with our variables here. We can also say z sub x, not z sub x. We can also, here's our new symbol, our partial derivative, curly d, with respect to x. fxy, and we just call it d, but the curved d means we're doing a partial derivative. We also write dz dx, and let me put an equal sign there, and that equals df dx. All of these notations are equivalent. The subscript notation and the d dx notation, all of them are equivalent. And this is equal to the limit, that's why we talked about limits at first, delta x approaches 0 of f of x plus delta x, comma y, minus f of xy, over delta x. So we're treating y as a constant, and we're taking the derivative with respect to x. Now, in your homework, you evaluated some of these limits for simple functions, and hopefully, I hope some of you recognized that what you were doing when we were doing limits in this form was like the definition of the derivative. And that was kind of the purpose of doing those, was to evaluate some of these limits. With respect to y, we're treating x as a constant. Our notation, we're going to write exactly the same notations, except we have a y instead of an x. And we'll use these all kind of interchangeably. And this is the limit. Same limit, except rather than x changing, y is changing. Limit as delta y approaches 0 of f of x comma y plus delta y minus f of xy all over delta y. So that's our definition of our partial derivative. And the idea here is that we are taking the derivative and treating one variable as a constant. When we evaluate our first partials, we call them first partial derivatives. Usually we'll just call them first partials. We'll talk about first partials, second partials. And tomorrow, or a block day, we'll talk about what we call mixed partials, because since we have a function of x and y, when we do a second derivative, we could take the partial with respect to x, and then the partial with respect to y, the partial with respect to y, then the partial with respect to x. So when we do higher order partial derivatives, we can kind of change the orders around, and interesting things happen there. So when we evaluate these at a point, when we evaluate our partial derivatives at a point, our notation, we're going to say point x0, y0. Our notation for evaluating our partial derivative at a point, we're going to write, for example, the z dx evaluated at x0, y0. So that's what that notation would mean. We would also say f sub x at x0, y0. We could also say this is not equal. And for our partials, I'm just going to say and our, let's say dz dy for our partial with respect to y at x0, y0. And that's the same as writing f sub y at x0, y0. So this is our notation for evaluating our partial derivative at a point. So we want it at a specific point. So what we're doing is to find our partial with respect to x, we consider y a constant. And we just treat it as a constant in our derivative. And to find f sub y, we consider x a constant. So we treat x in our, whatever our function is, we treat x as a constant when we take our derivative with respect to y. And we only do our derivative with respect to y. So what this means graphically. I always like to bring this back to what we're talking about graphically, what we're talking about geometrically, what's happening with our surface. So here's our, I'll draw a couple of coordinate systems and a couple of surfaces, and we'll show what we're talking about with these two partial derivatives, what they're telling us about the surface. So here's our surface up here above the xy plane. And I'm going to draw a curve on this surface. And I'm going to project this down onto the plane. So this is the line y equals some constant, y equals y0. The partial derivative with respect to x gives us the slope of this curve. So we're only moving in the x direction for some constant value of y. So the partial derivative with respect to x gives us the slope of this curve. So the slope of this curve as we're moving in the x direction. And then if we draw the same surface over here, so there's my surface. I'll do this one in blue. So we're going to take this curve on the surface, project this down onto the plane. And this line is x equals some constant. So x is constant. Our partial derivative with respect to y gives us the slope of this curve. So as we're moving along, only in the y direction, parallel to the y-axis, x is some constant, we're going to get the slope of that curve. So that's what our partial derivative with respect to y gives us. So geometrically, that's what our partial derivatives are giving us. And where we're going to go with this is, so analyzing our curve, thinking of the rate of change in the x direction, rate of change in the y direction, that's going to give us some tools to work with for our surface. We can tell how the surface is behaving. We'll be able to do maximum and minima problems with our partial derivatives. Where is our surface at a maximum? Where is it at a minimum? All the things we've done with derivatives in single variable calculus. We will also be able to add some vectors to what we're talking about and talk about the rate of change of our surface in any arbitrary direction. So we can talk about the rate of change in the direction of any particular vector. So any direction, so that's the other thing that we'll do with this. And we'll use these partial derivatives to talk about the area of a surface. It'll give us a way to work with the area of a surface, find the area of a surface. So we'll integrate and talk about areas. And it'll let us do some other things. So the important things from this first part, partial derivative with respect to x, consider y a constant. Gives us the slope of this curve, moving only in the x direction. Partial derivative with respect to y, we consider x a constant, and it gives us the slope of this curve as we move only in the y direction along the surface. So what I want to do is spend a little time kind of visualizing partial derivatives, the signs of partial derivatives, talk about increasing and decreasing when we're looking at a picture of a surface. So keeping this in mind, this idea of slope, I want to look at this next page. So here's our surface. Oops, that's not what I wanted to do. Here's our surface. Let me make this a little bigger. And what we want to do is, for all of these, for A, B, C, and D, we want the sign, and I'm talking about positive, negative, of these partial derivatives at these points. So for the first one, we want the sign of the partial derivative at the points 4, 1. So the sign positive, or negative. What I usually think of with this is, for the sign, are we going uphill or are we going downhill as x increases or as y increases? So part A, we're here at the point up 4 over 1, so we're at this point on the surface approximately. If we're moving in the x direction, positive x direction, does it look like we're going uphill or downhill? So we're moving in the positive x, so we're moving that direction. Going uphill or downhill? Looks like we're going downhill. So that sign would be negative. So our partial derivative with respect to x would be negative because we're going, our function, our surface, we're going downhill. Our function is decreasing as x increases. Part B, f sub y at this same point. As y increases, so we're going this direction. As y increases, are we going uphill or downhill? Uphill. So that would be positive. So our partial derivative would be positive because as y is increasing in that direction, as we move in the y direction only, our function is increasing. We're going uphill. How about f sub x at negative 1, negative 2? So that's a little, so here we're at negative 1 and over negative 2. So we're at this point in the xy plane. As x is increasing, is it going to be positive? Is our partial derivative going to be positive or negative? As we're going this direction. Negative. We're going downhill. Our function is decreasing as we move in the positive x direction there, so that's going to be negative. And then finally d, f sub y. So if we move from that point in that direction, in the positive y direction, uphill or downhill? Downhill, so that's going to be negative. So just a little bit of practice thinking about the sign positive or negative of our partial derivative. Now these next ones are a little more challenging. Next ones have a graph of the surface, and then it has graphs of the partial derivatives. Partial derivative with respect to x and partial derivative with respect to y. So we want to look at the graph of the surface and then identify which graph is the graph of the partial derivative with respect to x and which one is the partial derivative with respect to y. So here's our surface. First off, what kind of surface is this? What do we call this surface? Saddle? Or what was the other name we used? What's this shape? Right? So this is a parabola. This direction along here we have hyperbolas. So this is a hyperbolic paraboloid. Saddle. We'll use the word saddle in another context as well. And it'll help to visualize this. All right, so now we're looking at these two graphs. And we want to know which one of these, A or B, represents the graph of the partial derivative with respect to x, and which one represents the graph of the partial derivative with respect to y, when we want to know y. So this graph is going through the x-axis along here, and it's slanting from the positive. It's up above the xy plane here and below the xy plane here. This one is going through the y-axis right here. So which one is going to represent partial with respect to x, and which one is going to represent the partial with respect to y? Any ideas? So here's how I looked at this one. Let's just look at the partial, let's look at along the line, along the x-axis. The partial derivative with respect to x over here is positive or negative? Negative. And then at the origin, it's 0. And then, is it positive or negative here? Positive. And it's going to keep, here it's going to keep going this direction, here it's going to keep going this direction. So the partial with respect to x, as we move in the positive x direction, moves from negative to positive. So which surface, A or B, as we move in the positive x direction, goes from negative to positive? B. Here, this is saying the partial derivatives are negative because it's down below the xy plane. Z is negative, and here it's positive. So B would be, this would be the partial with respect to x. And then if we look at this one, the partial with respect to y, as over here in the negative y, over here where y is negative, we're going uphill until we get to the origin, and then over here we're going downhill. So it goes from positive to negative. And when we go through the x-axis is where it changes. So here we're positive, here we're negative. So that's going to be f sub y. Now this next one is a little trickier. So here's our surface, and we want to know which one of these, A or B, is a partial with respect to x, and which one is the partial with respect to y. So which one of the partial derivative graphs looks like it's going to be easiest to analyze? A. That looks like an easier graph. So take a look at graph A and see if using the ideas, kind of the ideas that I talked about there, see if you can figure out whether that's a partial of x, f of x or f of y. Anybody have any ideas? All right, let me give you a hint. Looking at this surface, thinking about, because it looks to me like more happens in the y direction, I'm going to look at the x direction. What is the sign of the partial derivative with respect to x on this entire surface? It's positive, right? We're going uphill. No matter where we are moving in the x direction, we're going uphill. Which one of these graphs, A or B, is always positive? A is always positive. So this would have to be f sub x, because the derivative with respect to x, we're always going uphill as x increases. The derivative with respect to x is always positive. And where is, let's see, and it's, where is the derivative the greatest in magnitude? The derivative with respect to x, the greatest in magnitude on this surface? Isn't it right along the x-axis? Isn't that where we're going the steepest uphill? Anywhere off the x-axis, it's a little less steep. Here on the x-axis, the partial with respect to x is the greatest in magnitude. Along the x-axis, the partial with respect to x is the greatest in magnitude. So that would be partial with respect to x. So that leaves this one to be the partial with respect to y. And we can see the partial with respect to y, positive here, negative on this side of the x-axis, positive here, negative here on this side of the x-axis, so that would help us think about that one. Negative here, positive on the other side of the x-axis, so that would help us with that one. So these partial derivatives give us another tool to work with these surfaces, to think about these surfaces, to visualize these surfaces. All right, so let's do a couple of examples of calculating some partial derivatives.
Yeah, I wish we could pick them up on screen.
Now, in your textbook, like I said, in the interactive textbook, some of these homework problems have interactive graphs where you can click on a button and it brings up a graph like the ones I put on the screen, and you can rotate them around. If you have those of you with the Apple computers, that 3D graphing software, if you can graph these surfaces, it can really help you visualize what's going on with them. But the online textbook does have some interactive graphs on some of the problems. It has a blue button next to the problem, and you can click it and get an interactive graph. All right. So here's our surface for this one, and for this example, we want the slope in x direction at the point. So we want the slope in the x direction and the y direction at this particular point. So there's our graph of our surface. So before we do anything, the slope in the x direction is what's the problem asking us? What is it asking us to do? If it's asking for the slope of this in the x direction. Partial derivative with respect to x, partial derivative with respect to y. So first, let's take a look at what we just were doing. In the x direction here, as x increases, should our partial derivative be positive or negative? As we increase, as x increases, are we going downhill or uphill from this point? Downhill, so we should have a negative partial with respect to x, and we're going uphill or downhill as y increases in the y direction. Downhill, so both of them should be negative. So we know that both of them should be a negative. So let's calculate our partial derivative. So we're going to do dx of h xy. We're going to take the partial derivative with respect to x, keeping y constant. I just get 2x. I take the derivative of x squared, I get 2x. Y is a constant. Partial with respect to x of a constant is just 0. So I get 2x. And then I plug in at the point. Here's our point. Our point is at -2. X is -2. We get it equals -4. So what that's telling us is for every unit we move in the positive x direction at this point, we're moving -4 units in the z direction. We're decreasing in our height at -4 units for every 1 unit we move in the x direction. And then our partial with respect to y of h of xy. We consider y a constant, or sorry, consider x a constant. So the partial with respect to y of a constant is 0. So I get -2y. And at our point, we get, plug in y equals 1, and I get -2. So in the y direction, we decrease in height 2 units for every 1 unit we move in the y direction at that particular point. Questions there? All right, let's do another partial derivative without a surface this time. A little more complicated partial derivative. Z equals cosine 2x minus y, and we want our partial with respect to x. We want f sub x and f sub y at the point pi over 4, pi over 3, square root of 3 over 2. All right, so let's find our partial with respect to x, dz dx. So what's going to be dz dx? Negative sign, that's a good start. Negative sign of this whole thing, 2x minus y. And then we're using our chain rule times the derivative of the inside function with respect to x, which is 2. So I'm just going to put that out front. Minus 2 sine 2x minus y. And then I'm going to plug in my x and y here. So at the point, we get minus 2 sine of pi over 2 minus pi over 3. And when I evaluate that out, I get -1. And then our partial with respect to y, dz dy. We know we have to start out with a negative sign. And we have this whatever is inside, minus 2x minus y. And our partial of the inside function when we do our chain rule with respect to y, -1, so that goes away. And then we evaluate that at our point. And so we get the sine of pi over 2 minus pi over 3. And when we evaluate that, simplify that, we get 1/2. So questions on finding our partial derivatives there? All right. One last question to talk about. So we want to find for f of xy equals 3x to the third minus 12xy plus y to the third. We want to find where f sub x equals f sub y equals 0. So we want to know where the first partials with respect to x and with respect to y are 0 simultaneously. What would you guess would tell us about the surface? A maximum or a minimum, where our partial derivatives, our first partial derivatives, are both equal to 0 at the same time? Turns out that that's exactly the case. But because we have a two-variable surface, maximum and minimum kind of take on we have to do more analysis than just the first derivative. Because let me go back here really quickly. Is that point right there, right at the origin, is that a maximum or a minimum? How about moving in the y direction? In the y direction, it's a maximum. In the x direction, it's a minimum. So we get some interesting things happening there. We call that a saddle point because it's right in the middle of our saddle. And we'll be able to find saddle points analytically with our partial derivatives. We just need a few more tools first. But for now, we just want to find where these two equal 0 simultaneously. So let's calculate our partial derivatives. Partial derivative with respect to x. What are we going to get? 9x squared. We're going to take the derivative of this with respect to x, and we get minus 12y. Derivative of this with respect to x? 0. Constant, so it's 0. F sub y, partial with respect to y. Take the derivative, that's a 0. We get a minus 12x plus 3y squared. So we want these to equal 0 simultaneously. So I'm going to look at this first equation. So I'm going to say 9x squared minus 12y equals 0. That means that 3x squared equals 4y. And from this one, I'm going to look at that equation, and from this one, I want 3y squared equals 12x, and I can solve this and I get x equals y squared over 4. And I'm going to substitute this in for x. So I set both of these equal to 0, substitute, and I get 3 times y squared over 4 equals 4y. And from this one, when I solve this one out, I get this y squared over 4 should be squared, yes. Thank you. So from this one, I get 3y to the 4th minus 64y equals 0 when I solve this out. And so that tells me that y, I'm going to factor out a y, times 3y to the cubed, 3y cubed minus 64 equals 0 to the cubed, yeah, inventing new language here, to the cubed. So y equals 0, or y equals 4 over 3 to the third. And then I substitute back in here to find x. That tells me that when y equals 0, that tells me that x equals 0. Or, and when I plug this in for y, I get x equals 4 over 3 to the 2/3. So our points are 0, 0, 0, 0, and 4 over 3 to the 1/3, 4 over 3 to the 2/3 is where these two equal 0 simultaneously. And then let's look at a graph of that surface. So there's a graph of that surface, and we see our saddle point, and because of this cubic surface, we end up with a couple of points in that saddle that are at the same height. So there's our surface. So this one's kind of a hyperbolic paraboloid, but we have this cubic thing going on in there, so that makes it just a little different. All right, questions on first partial derivatives? So next time we'll talk about higher order partial derivatives, second partials, third partials, etc. And like I said, when we have multivariable functions, we can change the order of things, and different things happen with our mixed partials, what we call our mixed partials. We'll talk about chain rules, because we have, if x and y are a function of some other variables, we get all kinds of chain rules that happen with partial derivatives. And then we'll start applying partial derivatives to actually solving different kinds of problems. All right. All right, there we go.